Hey guys, this is Isaac again, and today we have a coalition of objects, or in this case, cars, which is going to be a totally inelastic problem here with us today. And this is going to be a very realistic problem that happens a lot, that we see once, we're driving in the freeway or highway or just in a regular street. So I have two vehicles here. I have a pretty big truck on my left hand side and a small compact sports car. In this case, we have, I think that's a Mini Cooper or something like that, driving. And these two vehicles are driving head on head, and they're going to collide right in the center. They're going to have a collision here, and they're going to stick to each other. And we're interested in finding the final velocity of the both vehicles attached or stuck together as they collide with each other. So I'm going to denote some values here. I'm going to put truck, and I'm going to say that the mass of my truck, and I'm going to put a small t there, the mass of my truck is going to be, let's say, 1800 kilograms. And let's say that the car here, let's say that the mass of the car, I'm going to put MC, equals 900 kilograms. And again, these are just synthetic numbers for the simplicity of our problem. And let's say that the truck is traveling with a velocity of 15 meters per second to the right. So I'm going to put a plus there. And the velocity of the car is traveling at minus 18 meters per second. And I put a minus because he's going on the opposite direction. So we're interested in finding. So I'm going to say, what is the final velocity? Okay, so we're going to dive right into the problem. So I'm going to have to denote my momentum. Again, my momentum is going to equal to the mass of the truck. This is before collision, the mass of the truck times the velocity of the truck before collision plus the mass of the car times the velocity of the car before collision, and that is going to equal. Remember that we have two vehicles that are going to hit each other, and they're going to stick afterwards, so they're going to stay stuck together. So we denote that as totally inelastic collision. So now on our momentum, after they hit each other, their masses are combined because we're going to treat it as one object. So we have momentum after the crash is going to be the mass of the truck plus the mass of the car, and that is going to have a velocity, and I'm gonna call that as a velocity combo. Right, velocity combo. That just means that the velocity of the truck and the car combine after they collide. So I'm gonna put some numbers. I'm gonna put my numbers in, and all of this is just going to be equal to the mass of my truck was 1800, and the velocity was 15 meters per second, plus the mass of the car was 900, and my velocity was minus 18. Right, and all of that is going to equal to the masses added together. So the masses, we had 1800 from the truck plus 900 from the car, and we're trying to find the velocity, and I can put a symbol there, so combo. We're trying to find the velocity of both of them after they collide with each other. So let's simplify our numbers, and on this side we're going to have 1800 times 15. That will give us 27,000. 900 minus 18 should give us 16,000. 16,200 actually. So 16,000. That should be a 2. So let me rewrite that. 16,200. And all of that is going to equal to 1800 plus 900. That will be 2,700. And I'm going to put that, and I'm going to put a V combo. Alright, so let me simplify this for a minute. Over here on this side, 27,000 minus 16,200, that will give us 10,800. And we're going to divide, and so that should be equal to 2700. That should be 0 V combo. So we divide both sides by 2700, and we divide this side by 2700. That cancels out. So our V combo equals, that should be 10,800 divided by 27. We get 3, put 4. We get a positive 4.0. We can round meters per second. And this is our velocity of both objects as they hit each other. So what does that mean? So that just means that as this truck collides with this vehicle, after they hit each other, they're still going to move in the positive direction at 4 meters per second. Notice that the velocity of the truck is a lot smaller than the velocity of the vehicle. However, because the vehicle has half of the mass of the truck has a greater momentum. As you can see here, it has 2,700,000 kilograms per meter per second. This is momentum, and the vehicle only has 16,200 kilograms meters per second of momentum. So the truck has a greater momentum than the vehicle, and as they collide with each other, the momentum of the truck is going to dominate. So they're still going to move in the positive direction at 4 meters per second. So 4 meters per second is going to be the velocity of the crash, or the velocity after they crash, and the distance that they're going to move for a certain amount of time. Now, of course, we don't have here the coefficient of friction, but if pretending we didn't have any force countering that, or we didn't have, let's say this was ice, and we ignore the coefficient of friction, they will move infinitely for 4 meters per second until a greater force, or let's say this tree stops them, right, until they hit this tree or something. So that's just the way it'll work. And we can also compute the kinetic energy of both the truck and the vehicle. So I'm going to go ahead and do that. I'm going to clean the board. I'm just going to write my answer up here, and let me pause the video so I can clean up the board and then continue. So now we want to find the kinetic energy before and after the collision. And notice that I wrote our previous answer up here, the 4 meters per second. So let's find the kinetic energy of before and after. We know that the formula for kinetic energy is 1/2 mv squared. So let's find the kinetic energy before the crash, and that is the truck kinetic energy. So I'm going to put that K truck plus K of car. Alright, and the kinetic energy of the truck, so it was 1/2. The mass of the truck is 1,800 times its velocity 15 squared, plus the kinetic energy of the car, which was 1/2, and the mass of the car is 900, and its velocity was minus 18 squared. Notice that the minus 18 is going to become a positive because we're squaring the number, and that should give us approximately, let me use my calculator here and you can follow along. So I'm going to pop. That is going to equal 300,488 joules. So 348,300 joules, and we can just denote that as 348 kilojoules, right? So this is our kinetic energy before the collision. So that will be this will be our kinetic energy before the collision. Now, what is the kinetic energy after the collision? So after, notice that now we don't have both masses independent from each other, but we have a combined mass, and we also have a combined velocity. So our kinetic after is going to be, again, K equals 1/2 mv squared, and that is going to equal 1/2. Our mass was 1800 plus 900 of the truck and the car, and all of that is going to be times our velocity squared, which was 4 squared, and that should give us approximately, let me do that. That is going to be approximately 21,600 joules, or we can rewrite that as, we can round it and say 22 kilojoules. So the change in our kinetic we can denote as change in kinetic, and that will be kinetic 2 minus kinetic 1, and we will have that to be, remember that this was our K2, so we will have 348 kilojoules minus 22 kilojoules, and that should give us our change in kinetic energy, which will be 326 kilojoules. So the change in kinetic energy was 326 kilojoules. So this is the energy that we lost in the coalition. So where did all this kinetic energy go? Think about it for a second. We started with 348 kilojoules, and we ended with 22 kilojoules. So where did the 326 kilojoules difference go? Well, in a coalition, you have bending of metal, you have parts coming and flying everywhere. So, but just the energy that it takes to bend the metal is what ate up this conserved, or this kinetic energy, the change in kinetic energy. So the bending of the metal takes work, which was the change in this kinetic energy. So I hope you guys enjoyed this problem. It's a very realistic problem, and it actually puts all the components together. So this was a coalition of objects, totally inelastic. If you enjoyed this problem, please share it with your friends, comment, rate, and subscribe.